for this book. So just go here and write the name of the book. Then it should be okay. But now you can find the book there. In the weekend, I went through your answers for the previous exercises, and I was really impressed by the quality of your answers. You have really done quite a lot of work, which is of course very nice. And we have still this week and next week we have the last lectures, and there will be only one exercise more for the data storage, and that's it. So there is one exercise I have to build here for week 7. Today we are discussing about the training models, and for the data storage there are two quite easy questions for week 5, and then there will be, these are old ones which you can see there. Yeah, only one task for data storage for week 6 because we are running out of time. And it's okay if you can't do one of the exercises. You don't have to do everything to pass. If you can do something, you don't have to submit anything, of course. If you have done most of the exercises, your grade still will be very high. I have been quite easy in giving points. But we go to training models today. And we have discussed at some last time about the gradient method and such things. But we go a bit deeper today. So these training algorithms have been like black boxes. And much can be done without knowing about anything under the hood. However, you need some understanding about the algorithms which are beneath, under the hood. And we today take a look at the regression models. Both models that can be computed analytically or closed form, like the first order linear equation, like line equation. Or in general, polynomial equations can be solved in closed form. And then there are these iterative approaches like the gradient descent, where you gradually go in the minimum direction of the model parameters to minimize the cost function. There are quite a lot of mathematics here in vector and linear algebra and matrices. I will explain something, but you can skip those if you don't like mathematics very much. So what is a linear model? You should now remember these a few terms here. This is a linear regression model equation. So you have some constant term theta 0 plus some model parameter, a bias term, times the x value So this is a vector containing x1, x2 until xn, and these x values have some constant value which multiplies these x's. So the predicted value this linear regression model predicts is this y with the hat above the y letter. N is the number of futures we are predicting or using in the prediction, and this x is the future value, and the theta is the model parameter, and these are the feature weights. These are constant values that are multiplied with the x's. And in vectorized form, it's much simpler to write this like here. So now we have two vectors which get multiplied by the point dot product operation. There may be such a, I think at least our foreign friends, you have studied quite a lot of mathematics, so these things probably are familiar to you, but I think the Finnish students haven't studied mathematics so much, so there are very much strange symbols here. But don't, it doesn't matter. Hopefully you get the idea anyway. I know that the mathematical education in for example in Eastern Europe and China, India, is at very high level compared to Finland nowadays. So theta is model's parameter vector, and x is the instance's future vector containing the x's. This theta contains the thetas, and this is a dot product, which gives the sum of these two. And this is some hypothesis function that uses these model parameters. So in machine learning, the vectors are often presented as column vectors. So column is in up-down direction numbers, and row vectors are horizontal, and sometimes in this math they transpose the vector. So transposition changes the column vector into row, and the reason for this is that when you multiply row and column vectors, you get a single number as a result. And that is much easier to use in the analysis. You have only one number as a result. Okay, there is some very complex math here, but the basic idea here is also, as we discussed before, that we minimize either the root mean square error between the observations and the function, either the root mean square error or mean squared error. They only differ by the exponent of 2. The other uses 2 exponent 2, and the other uses absolute value of these terms here. So in here the theta times x is the function we are searching, and these y's are the observed values. In any case, it's easier maybe to see this data set. Now this is a randomly generated XY data set, and then the easiest method here is to find the linear model. The original data was generated using this kind of formula. Y is 4 plus 3x plus some Gaussian noise, and now the algorithm predicts the values for the constant part 4.2 and for the slope 2.77. So in ideal world, we would of course we would get the values 4 and 3, but because there is quite a lot of noise in this data set, we get something else. And now when we have this functional form, this is just a linear equation, constant plus slope times the value of x. Then of course you can predict values, any value using this formula. You can take any value of x here in this range and you get the corresponding y value. And here is the basically the model is a red line that best fits into the observed data points. So there are ready-made functions in this scikit-learn package which calculates, for example, the least squares function can be found there. So for example, here you just input the x's and y's and it gives you the result. There is such a complicated math. For example, I didn't know about the pseudo inverse of x. I have studied linear algebra in the university very long time ago, but I didn't know about that. So let's skip it. So anyway, the basic idea of the linear regression is of course very simple. Then the gradient descent was what we discussed previously, which is the iterative method. You take steps towards the minimum until it doesn't change or it begins to grow. The important parameter here is the size of the steps you take. If the step is too small, it takes very long time to reach the minimum, of course. And usually it's working like this, that the step, when you go near the minimum or the gradient value becomes smaller, then the step also gets smaller. And the value we are looking for is this theta and this hat above. So of course the gradient is larger negative number, the steeper the slope is. And here, when it's almost horizontal, then the gradient is small, and then also the step is small. Step or learning rate. They are talking about learning rate in this text. Then if the step or the learning rate is too high, it happens that when you calculate the gradient here, it goes here. Sorry, it starts from here, and then it starts to diverge. It doesn't converge towards the minimum at all. In this case, it doesn't find the answer at all. When you have a more complicated function, you can get this local minima. So in this case, the algorithm finds this local minimum, which is it's not the global minimum. And to avoid this, you can use this stochastic gradient descent, which can hop around this hill here and find this global minimum. It comes here a bit later. But fortunately, if our function is no, it's not important to find the local minimum. It's important to find the global minimum. And the point is that sometimes this algorithm doesn't work very well, and it finds this local minimum and gets stuck there, because it goes always towards the negative gradient. And now if it calculates here the next step, it goes uphill or positive gradient, and then it stops and decides that this is the global minimum. But it's not true. The global minimum is here, but the algorithm can't find it. The global minimum is what you are looking for. And in this case, if you happen to start the iteration from this side, from the right, then clearly this happens to find this global minimum. Fortunately, if you have a linear regression model, meaning one line, you have only one minimum in this dataset, which is the constant plus the slope. And you always find it. So the gradient descent is guaranteed to approach the global minimum always. But in this case, when the model function is so simple, it is faster to calculate. I guess it's faster to calculate always it analytically, because there are quite simple formulas, at least in 2 dimensions. Then if you have very n-dimensional space, then you maybe you can't calculate it analytically. Okay, we are looking for always, we try to find some function, some model function which fits the data, observed data set the best. That is the global minimum. For example, here, this red line is in the global minimum. But in practice, the data set is much more complicated. It has many dimensions. Here we have only 2 dimensions, X and Y. But in machine learning, more complicated machine learning applications, we may have 100,000 or many hundreds of dimensions of the data. And we have to optimize a very complicated plane. So then it is not possible to visualize it in such a simple way. But the idea is the same, that you find some mathematical function that fits the observed data by varying the values. For example, here you could start to guess the values for the slope and the constant value, and change those values until you get a line that best fits to these observations, these blue dots. So the global minimum in general is a situation where these model parameters fit the data the best. So mathematically, this is done by doing the partial derivative. If you have many variables in your model, you have to differentiate every one of those and take the direction of the derivatives and always go to the most negative direction. And instead of calculating this separately, like here, each term in the sum, you can calculate it in one vector, in one gradient vector at once, which is faster. And this is called the batch gradient descent. So maybe these images explain the thing a bit more. You have the observed data here, and then these blue lines are different lines that try to fit this observed data the best. If you have this data step too small, you never reach it, or it takes a very long time to get this line fit the data. And if the step size is too small or too large, then it goes away without getting the data. So from here to here, and it skips the data. And in this middle, the learning rate or the step size is good. And there are algorithms that in this scikit that determines the or can determine the suitable learning rate. Okay, the stochastic gradient descent is more, it takes a random direction. So in a general case, it can hop over the hills in the local minima. So the stochastic gradient descent picks a random instance in the training set every step and computes the gradients based on that single instance. It's very fast, and it can train huge data sets. But it usually finds with some accuracy the minimum here in the center of this image. But it doesn't stop automatically. Or once the algorithm stops, the final parameters are good but not optimal. So in this case, when fitting the linear data set or linear function to this data set using stochastic gradient descent, you see the steps are highly irregular. Here are very large steps, and then there is very small step here, and it's more or less random. So in general, it more or less randomly changes these, in this linear case, the constant and the slope. But magically, it still finds the optimum result. Okay, I think I skipped some of these. Then the polynomial regression, of course, it's, for example, second order polynomial, which clearly fits this dataset better than linear. You see the functions there, and here you see the result, the polynomial fitting. So this array contains the constant term 1.78, then the first order coefficient 0.93, and the second order coefficient 0.56. And here you see the original function which was used to generate these blue dots. So again, the noise makes it not perfect. The result is not perfect with the noise. So here are some examples of different polynomial using different polynomial degrees, and the same data set. If you use linear model, this clearly is not good. And in this case, we say that this model underfits the data, and we need a more complicated model like a second order polynomial. to fit the data correctly. And here the second order polynomial, the blue dashed line, goes quite nicely. But if you add more degrees to the polynomial, it goes through almost all the data points, and this is not, clearly this green line is not reasonable. And in this case, it said that the model is overfitting your data. So the model is too complicated for this dataset. So in order to estimate if you are under or overfitting your data, you can use so-called learning curves, which are the plots of model's performance on the training set. The training and validation sets are data sets from the same data. They are separated from each other. You see in this code, for example, where it was. And this validation set is different from the test set. The test set is independent set. That when you have optimized your model, then you use the test set to check if it can evaluate or predict the values correctly. And this is called cross-validation. So here, train test split, I guess that one. Here you separate the prediction and validation datasets. As you see, they are from the same data, just separated for the mathematical purposes. And when you change the training set size, for example, here from 0 to 80, so how many data points you have in these sets, you see that these training and validation sets, the RMSE is quite large. When you increase the set size, and in this case, it is said that this model is underfitting. Why is it underfitting? Because this RMSE is too high, and the validation and training sets are close to each other. So I was reading this text here. And okay, here it said the learning curves are typical of model that's underfitting. Both curves have reached a plateau. They are close and fairly high. So if your model is underfitting the data, adding more training examples will not help, as you see here. Training set size increase doesn't work. So you have to use more complex model or come out with better features. And this you see here, this is underfitting. And adding second order degree polynomial solves this problem. And here you see results of overfitting. In this case, the error on training data is much lower, and there is a gap between the curves. In this case, the model performs better. The smaller the error, the better is of course the result. When this is small, then the mathematical model describes the observed data very well. So now there is gap between the curves, and the model performs better on the training data than on the validation data, which is the hallmark of an overfitting model. And if you use much larger training set, these curves would converge, so they would go closer to each other. And one way to improve an overfitting model is to feed it more training data until the validation error reaches the training error. One way to reduce the overfitting is to regularize the model. So there is some term that is added to the cost function. And there are rich regression, lasso regression, and elastic net, which is a combination of these two. So in this case, this is the mean square error, and it gets added this kind of formula where this constant alpha describes how the regularization of the model works. If alpha is 0, then this ridge regression is just linear regression, so this term goes away. When this alpha is very large, then all the weights end up very close to 0, and you get a flat line through data's mean. You can see the effect of alpha. I'm not going into detail of this, what this means mathematically. You just we need to know in this course that there are ways to make this regression better by adding some restrictions to the model, which can be controlled with this parameter alpha. So when alpha is 0, this is the blue line, is exactly the same as previously the linear line equation. And when you add alpha, medium size alpha value, then you get this green line. And the larger the alpha, the closer this fit goes to constant value. This is close to the average value of all these data points. And in the okay, here's the polynomial model. It's quite a high degree of polynomial because it goes through several minima and maxima. But in this case, using alpha value of 1 gives quite a good fit to the observed data. So we don't have to care too much about the mathematics here, but because there are functions done for us that can do this. Another possibility is the Lasso regression. It's almost the same, but this cost function term is a bit different. Here you see that theta is the absolute value, while here it was a square. Otherwise it's the same, and there is a factor of 1/2 difference, but basically very much the same. And again, controlling the alpha value, you can control how this fitting of the function to the model data works. In this case, it seems that this middle green alpha line here gives the best fit to the data. For example, the dashed line in the right-hand plot in figure 418 looks roughly cubic. All the weights of the higher degree polynomial features are equal to 0. In other words, this Lasso regression automatically performs future selection and outputs a sparse model where there are only few non-zero values for the future weights. Okay, I'm not going through all this material here. The early stopping, that means that when you have the training set and validation set and you do more iterations, I think the epoch is the number of iterations you have made. And when you first the error is very large here when you have small number of epochs made. But then it decreases quite rapidly until you get a point here. This training set error goes very low in smaller values, but this validation set reaches a minimum here. So here you get the best model. When the validation error starts to increase, then you know you have gone too far. You are overfitting. This is called early stopping. So gradient descent is to stop training as soon as the validation error reaches minimum. Just a few words about the logistic regression. Here we have basically a method to model the two options. Either something is true or false. You see the function shape of the function here. Here the probability is 0, so something is not true, and here the probability is 1, meaning that something is true. This is called a sigmoid function. is an S-shaped function which is given here as a function of some variable t. So for example, here is an application of the logistic regression. This is a data set where the goal is to try to identify the iris virginica from these images. So this dataset contains images of 150 iris flowers of 3 different species. They have different these leaves are different for each of these different iris species. And the goal is to try to identify this one separate from these two others. So the question is the specific flower, is it iris virginica or not? So then you can use the logistic regression function. Here the dataset is loaded. So now the petal widths vary from 0 to 3 centimeters. And for iris virginica, they range, this petal width ranges from 1.4 to 2.5. While the two other flowers have smaller petal width from 0.0 to 1.8 centimeters. So it means this width of this petal. So when you determine the petal width, you get this kind of logistic expression. So definitely here on the left, the probability is very high that this is not iris virginica, and here is very probable that it is iris virginica. And in the middle, we are not sure. It can be either iris virginica or not. The squares are for the other flowers, and the green triangles are for the iris virginica. But when you plot it, the petal length and petal width in one plot, then you clearly see that there is clear separation between the iris virginica and not iris virginica in this logistic linear model. So once trained, this logistic regression classifier can, based on these two features, estimate the probability that the new flower is iris virginica, and the dashed black line here gives the boundary 50% probability, which is this model's decision boundary. And these other parallel lines represent the points where the model outputs a specific probability. Here it is 15%, and here it's 90% probability that the flower is Iris virginica. Okay, I'm not going to the softmax regression today. Hopefully you get some idea about regression. And I will update the exercises for both data analysis and storage. Hopefully, or I know that I have time now by the end of the week. I don't have to teach all the time, so hopefully I can do those. And I also update the links. And you can skip some of the exercises. You still get very high grade. You can have the grade 5 even if you don't have done anything or everything. So don't worry. Don't worry about that. And next week is the last lecture week. Then I try to tell something about the artificial neural networks and have some exercise related to that. Then for the last week of this period, there will be no more lectures, and you have time to finish your work for me and Teemu, and you have the Teemu's evaluations also during the last week. Okay, I don't have anything more to say today. If you don't have any questions, I wish you nice rest of the week, and see you next week.